Hey guys, how's it going? I'm going to ask you to be a little bit patient with me, but I'm going to try and do a little bit of a lesson from the book using my book here on the right and my drawing area on the left. The next simple machine we're going to talk about is the pulley. This is from the book pages that I shared with you in Google Classroom, so you can pull that up if you want to follow along, or you can just follow with me here on the video. So the definition for a pulley is really pretty darn simple. So you have this guy, and that's it. I mean, you guys have seen a number of pulleys all the time. So let's go on to the next page here. You've got pulleys that have been around for literally thousands of years. So this here is a kind of a complex pulley used in construction. This next one, B, is from a ship, you can probably tell. And this one is your traditional, simple, single fixed pulley. It's kind of hard to draw on this. So what is the definition of our simple pulley? The first thing that I want you to realize is that we have a load and we have an effort. Notice this thing here on the right, it says provides no mechanical advantage. So you might say, well, what the hell? Why would I want something that provides no mechanical advantage? Well, the biggest thing that's going to happen when we use a pulley is to reverse the direction of the effort. Now, so imagine if you've got this guy here that you're trying to lift, and you are standing here and you're trying to lift it straight up. Well, that's going to be pretty heavy. Now, is it the same effort if you are pulling up as opposed to standing here and pulling down? Well, it is going to be the same effort theoretically, but it is going to be a heck of a lot easier. You can probably hang on to this and bring down the rope and allow you to raise your weight with a little bit of ease, right? So it is a little bit easier. It changes the direction. So direction only, right? So changes direction only, and that's for a simple pulley. Okay, so let's go on to our next thing. So if we have a simple pulley, and let me go on to the next page, we have something a little bit different. So if you look over here, you've got a moving pulley. What's going to be the difference? Well, the difference is you've got, unlike this one where your pulley was fixed to the ceiling per se, this one is going to be moving. So you have your pulley. This is your load is hanging off of this guy here. This is going to be something called a support cable, and this is going to be your effort cable. And it doesn't matter whether you have the effort cable on the right or on the left. And the definition of ideal mechanical advantage, you have a couple of different ones. The first one is going to be the number of support cables, or just the number of supports. Now, how many do we have in this particular case? In this one here, I'm going to change color so we can look at it. We have one. This one doesn't count as a support cable because it is simply our effort, where we are pulling from. Now, what's interesting though is that if we change the setup, how do we have the pulley set up? We have one support cable here, and this effort one also doubles as a support cable because you are pulling on it. It is kind of, you're in a sense supporting it per se. It is kind of a little tough to understand, but just trust me that when you have a fixed pulley, you have an ideal mechanical advantage of one, but when you have a movable pulley, in this particular case, you have one support cable and two support cables for an IMA. Uh, uh, IMA equals to 2. So that is the first type of definition. The other definition for IMA is this one here. The length of the displaced effort cable divided by the load displacement. What the heck does that mean? So if I have my fixed pulley right here, we have our effort and we have our load. How far does this go? Right? And you're going to measure it, whether it be 1 foot or whatever it is, and versus how far this goes. The IMA in this particular case is going to be the length of the displaced effort cable, DE, over the length of a displaced load cable. How much does this go versus how much does this go? Obviously, if you have an IMA equal to 1, your displacement of the effort is going to be the same as your displacement of the load. And that's kind of pretty straightforward, pretty simple. I hope that makes sense. We also said that if we have a free moving pulley, here's a pulley, and there's our load, and here's our effort, we have an IMA equal to 2. IMA equal to 2 because we have 2 support cables. We have 1 support cable there, and we have 2 support cables there. So what if we combined the two? Right? We took the fixed pulley and our movable pulley and made it into one. And that's what this guy here on the right shows. This is called a block and tackle. It is not a football terminology, but what it does have is it has a fixed pulley and it has a movable pulley that is connected to our load. Our effort is still here, and we have our 1 support cable and our 2nd support cable. So we know that this particular setup here gives us an IMA equal to 2. That is called a block and tackle. You have your block right here, and you have your tackle right here. That's the name of it. So just keep that in mind. Now, can we take this to a larger degree and keep adding some? Well, yes, you can, and I'll show you that in just a second. Now, imagine this kind of a setup here. This looks like the block and tackle setup that we had before, where we had a fixed pulley and a movable pulley, but we actually have a bunch of them. And I suppose we can take this into infinity, but obviously it's not very practical. But what happens when we do that? Well, we said before that the IMA is going to be equal to the number of support cables or number of supports. Well, how many do we have in this particular case? So we're going to count them. So we have 1, 2, 3, 4, 5, 6. Now this one here is the effort, so it doesn't count. So the number of supports is going to be 6. So really our IMA is 6. And if we have a 60-pound weight, well, that kind of goes to it makes sense that the ideal effort, or the actual effort that we're going to put in ideally is going to be 60 divided by 6, which is going to be 10 pounds. That is going to be our ideal effort. And it kind of makes sense. Now, if you look at in the book, there's a page over here with a picture of Archimedes, this guy here. He's the same guy that famously yelled Eureka running naked through his town because he figured out how to weigh the king's crown without tearing it apart, figuring out that, how much gold is in it. He's also the same one that I told you earlier that he famously said, give me a lever long enough and a fulcrum on which to place it, and I can move the earth. So he can, in theory, stand here and pull down on this and move the earth. Now, of course, I think I mentioned that if you calculate it in theory, how long this lever would have to be, I think it has to be approximately 2 light years long. So that's pretty long. It's not going to really work. However, there is a pretty cool story that he was challenged by a king to move the ship all by himself. It says, move it from its place of construction, fully loaded, and move it by yourself. And here he is. And according to the theory, or to the story anyway, he set up a bunch of pulleys, kind of like this compound system that we had here, and was able to pull on it all by himself and get that ship moving. Now, he likely had quite a few more than this. According to this particular setup, he really only had 1, 2, 3, 4. He would have an IMA of 4. You really probably wanted a significantly higher IMA. If you think that a ship like this, I don't know, maybe weighs 100,000 pounds, and a single person can only maybe pull about a couple hundred pounds, so you just divide that out and figure out what his IMA would have to be. But regardless, this is what we have ideally. Now, what about the actual? So AMA is going to be different. AMA is going to be measured by a couple of different ways. Yeah, it's 60 pounds, and according to this, oh, it feels like 10 once you pull on it. Well, what if in real life, when you take into consideration the friction of the pulleys and everything else, it's going to feel more like 15 or 20. So instead of 10 pounds, this is going to be feeling more like 15 pounds or 20 pounds. Well, if it was 20 pounds, then really the IMA wouldn't be 6. It would be 60 divided by 20, which would be 3. And that depends on what they give you as part of the problem. And we're going to tackle one of those next as a finishing exercise. All right, let's finish up. This is on page 89 of your book. And let's go through the problem. This, you really have to know how to do this. I'm not going to trick you. I'm not going to change anything on the problem. The only thing I'm going to change is numbers. So you should be able to take care of this once we have our test. Yes, we're going to have a test on all of this. How are you going to make sure that I don't cheat? I can't, but I'm going to try my best to have you learn this. Anyway, so let's go through this. We have here our block and tackle setup, a bunch of pulleys, and the problem says that we have a 60-pound load and it's going to move a vertical distance of 10 feet. Okay, that's how much we are going to carry it. The actual amount of effort force that is needed to move the load is 15 pounds. Use this information to answer the following questions. Okay, so first thing we talked about is the IMA. What is the ideal mechanical advantage of the system? And it talks about the number of support cables. So we have 1, 2, 3, 4, 5, 6 support cables. That's this guy here, and our effort cable. So we have an IMA of 6, but they gave us an actual. So AMA is how much do we move versus how much does it feel like it's moving, giving you an AMA of 4. Next part of the question is how efficient is it? Well, we know that in the real world, efficiency is going to depend on friction, on real life situations, right? All kinds of things. This little guy here, I don't remember what the Greek letter is for that, but that stands for efficient. How efficient is this pulley system? Well, if we go ahead and divide the actual mechanical advantage by the ideal mechanical advantage, we have 4/6, or you have 2/3, or if you were to do decimal, it's 66.6%, right? And we'll go like this, 66.6%. So that is going to be your efficiency. Now, let's continue on. What is the ideal effort force that would be needed to move the load on the pulley system? Well, ideally, we said that if the ideal mechanical advantage is 6, and this thing weighs 60, when you divide 60 by 6, it equals to 10 pounds. But that was ideal. Actual, they give it to us, and it's 15. This is not 100% efficient. It is only 66% efficiency, and that kind of makes sense, right? What is the length of the effort cable that must pass through the user's hands to raise the load to the desired height? And this is the last thing that we talked about, where the other definition for the ideal mechanical advantage is the amount of distance that the effort cable travels divided by the amount of distance that the load cable travels. That means that you pulled 60 feet on one end in order to get this thing up 10 feet. It makes sense that you're not going to get something for free. You are going to be pulling on this right here. You're going to be pulling on this 60 feet worth. That's how much rope you're going to pull on it in order for this thing to raise 10. Does that make sense? I hope it does. So go through this on your own, read up a little bit, and if what I'm saying doesn't make sense, then ask me some questions. All right.